Okay, we're going to continue on here, chapter 16. Last time we started talking about acids and bases. And remember that really your definition of an acid is something that has the ability to produce H plus, or also, as we talked about in acid-base chemistry, H3O plus is the hydronium ion, and it is, to all intents and purposes, pretty much the same deal. They are used interchangeably in equations, also in formulas as well. While base is something that has the ability to produce hydroxide. So what we're talking about in this case is the ability to produce, for example, an acid. Free floating H plus is in the solution, while in a base, the ability to basically produce hydroxide ions that again are really free and kind of floating around in the solution, not necessarily attached to anything. A more sort of general definition of an acid and base is the Bronsted-Lowry definition that we talked about. And the Bronsted-Lowry definition, an acid is a proton donor. So that again is something that will give away an H plus, while a base is a proton acceptor, and it will accept that H plus. The sort of consequence of the Bronsted-Lowry definition of acid and bases is we do make pairs on opposite sides of the arrow. So for example, if we just show this here. In this case, this is going to be our acid. Water here will act as a base, which means it's going to accept the H plus over. The result of that is we will get a conjugate acid and a conjugate base on the other side. And we get these sort of acid conjugate base pairs, and they are related to each other by really the only difference, as we talked about, is that one H plus. So the only difference that we could have is that one H plus between those two. As the acid goes to the conjugate base, it has one less H plus. And as it goes from the base to conjugate acid, because it accepts the H plus, it has one more H plus. And again, that has to be really the only difference that is there, is that one H plus difference. Remember that the plus part of that's also important in terms of the conjugate acids and conjugate bases, as the charges will change because of the positive charge on that H. So you do have to adjust the charges like we see here. This guy was neutral to begin with. It gains an H plus, thank you, which means that it now becomes +1. This guy was neutral. It loses an H plus. So now what you're left with is, again, a -1. So the charge part of it's really important as well. We talked about the relationship of Kw, and Kw is basically the concentration of H plus times the concentration of OH minus. And for all intents and purposes, it is a constant value that you should know, which is 1 times 10 to the -14. And we could use that to calculate really the H plus concentration or the OH minus concentration. This is the acid part of the solution. That is the base part really of the solution. So we could compare the two concentrations, and if the acid part is larger than the base part, then it will be acidic. If the acid part and the base part are equal to each other, then it will be neutral. And lastly, if the acid part is less than the base part, or the base part is larger, it will be basic. So we can compare the concentrations and figure out if it's acidic, basic, or neutral. It's really the same calculation regardless of what you're given. You're basically going to take the concentration you're looking for, take 1 times 10 to the -14 and divide it by the other concentration. And again, you'll get what you need there. Any questions on that there? All right, so I think we're in the middle of an example here. Last time, this one, I think we did the first one before we left. So take a few moments there and knock out the other 3 here. So we're looking again for the opposite concentration, and is it acidic, basic, or neutral for each of these? So make sure you punch it in there. Make sure you use your exponent button as we talked about. And we'll talk about it here in just a second. Okay, let's take a look at each of these. So again, it's the same calculation here. So we got the H plus concentration, OH minus concentration equals 1 times 10 to the minus 14. So in this case, our OH minus concentration will equal 1 times 10 to the minus 14 divided by the H plus concentration that was given to us, 2.6 times 10 to the minus 8. As we talked about last time, you would definitely want to make sure exponent button in this chapter for sure on your calculator. So 1 exponent button negative 14 divided by 2.6 exponent button negative 8. And that is going to give you an answer of, looks like 3.8 times 10 to the minus 7. And again, it does need units of molarity as it is a concentration in this case. Any questions on that one there? Again, it may not give it to you on your calculator in scientific notation, may have zeros and stuff like that. When we look at it here, the H plus versus the OH minus concentration, which one's larger? It is the OH minus in this case. So remember that negative exponent, as we also talked about, is important. The smaller negative exponent is the larger number, again, because you're only going 7 places that way and put in a 0. Here you're going 8 places and putting zeros, so it makes a much smaller number. So in this case, it's actually OH minus is greater, so that should be basic in this case. Any questions on that there? Looking at the next one, pretty much the same calculation. So in this case, we're going to be looking for the H plus concentration, and that's going to be 1 times 10 to the minus 14 divided by 6.2 times 10 to the minus 9. Again, putting that in with our exponent buttons, and that's going to yield us a 1.6 times 10 to the minus 6 molar. Once again, here we'll compare the H plus concentration, which is the acid part of the solution, to the OH minus, which is the base part of the solution. And really, in most cases, all you have to do is kind of look at the exponent part here, and we see that, again, actually, in this case, the H plus is larger, and that would mean that this guy would be acidic in this case. Any questions on that one? And to finish this one out here, we'll do pretty much the identical calculation. H plus equals 1 times 10 to the minus 14, which again, you do need to know that as a constant value. 8.1 times 10 to the minus 3. Going to give us a 1.2 times 10 to the minus 12 molar. In this case, again, comparing our H plus to our OH minus, we could look at our exponent parts, and in this case, it's actually the OH minus, looks larger, and that would mean that this guy would be basic. Any questions on any of those calculations there? So I would say most people screw up on the punching into their calculator wrong. Yeah, so again, make sure you know how to properly punch it into your calculator. So let's take a look at a couple more here, maybe. Let's just calculate the OH minus here. So why don't we just do this? What is the OH minus in this one? And is it acidic, basic, or neutral? Okay, so looking at this one, it is the same calculation. So OH minus here going to be our KW value, our 1 times 10 to the minus 14 divided by what was given to us here, which is our H plus, 2.8 times 10 to the minus 5. And popping those guys in. Going to give us a 3.6 times 10 to the minus 10 molar. Once again, on comparison here, we got to the minus 10 to the minus 5. In this case, it is the H plus concentration that is larger, and this guy should be acidic as well. Any questions on KW or how to punch it in? So if you have the H plus or OH minus concentration given to you, you again can calculate the other concentration and figure out if it's acidic, basic, or neutral. Let's then talk about, we're going to skip this example, it's kind of the same deal. We're going to talk about the pH scale now and how to calculate pH. And This is not negative or anything, this is from PowerPoint, so that's the pH right there. So first off, the pH scale is a measure of acidity, and when we look at the pH scale, it runs from 0 to 7 to like 14. And if you are below 7, that's going to be acidic. If you're above 7, that's going to be basic. And if you're technically speaking at 7 on the nose, or darn really super close to 7 on the nose, that is going to give you neutral. 7 is sort of your middle point, if you will. So as you go from 7 closer to 14, you become more basic. And as you go from 7 down towards 0, you become more acidic in that case. The way that we measure the pH is pretty much the formula that's on the bottom. That's how we get to it, but it's not important for our class. So pH is equal to negative log of the H plus. So starting with this formula here, and pretty much the rest of them we're going to see for the rest of the chapter, how you punch it in will depend on the type of calculator that you have. If you have a display calculator versus a non-display calculator, again, if you're not sure which one you have, you can just hit log. And if it says log on your screen, you have a display calculator. And if it says error when you hit log, then you have a non-display calculator. So if you hit log, it says error, non-display. If you hit log, it says log, display. So display calculators, you pretty much roll the formula exactly the way it's written, and that is your negative button. You hit the log, and then you punch in your concentration, probably using your exponent button. So display calculators, you pretty much always kind of do the formulas exactly how they're written. That's exactly how you punch it into your calculator. If you have a non-display calculator, this formula and pretty much all the other formulas, you actually have to work backwards. So you would actually do the number first, you then hit log, and then you would hit your negative button. And again, if you have a display calculator, you would go in order negative button, log button, and then your number. So depending on which calculator you have as to how you kind of put it in there. Again, display, just like it's written, non-display, always working backwards in terms of how you put it in. Any questions on that there? Also important to make sure you do use your negative button and not your subtract button. Yeah. Does it say log when you hit log? Yes, then it's a display calculator. Yeah. Yeah, so if you hit the log button and it actually just says log on your calculator, then you have a display calculator. If you hit the log button and you get like an error message or an error, then you have a non-display calculator. That's pretty much, I say a lot of calculators nowadays are display calculators, but there's still some non-displays that are there. And that's a good way to kind of check if it is or not. So let's talk a little bit about pH. We do use the pH value to figure out if it's acidic, basic, or neutral. And let's talk a little bit about significant figures and pH. When you calculate a number like pH, the number of decimal places that your pH answer should have should equal the number of significant figures in the concentration. So when we're calculating pH from a concentration, however many significant figures there are in the concentration value is actually how many decimal places you should take your answer to. It also works backwards as well. So we're going to talk about how to go backwards in a second. But if you have the pH and you want to calculate the concentration, it goes from decimal places back to how many significant figures. So it is decimal places, significant figures. So why don't we give this a go here just to make sure we all know how to punch it in our calculators and the right sig figs. So what is the pH here of a solution that has this guy's concentration? So punch it into your calculator, see what you get, and then we'll talk about how we should properly display this answer. Okay, so at this point, you should see on your screen 5, I hope. Yes, so that should be the number that you see. Again, we would basically take the pH is equal to minus the log of 1 times 10 to the minus 5. Again, on the display calculator, the way you punch in, once again, would be negative button, log button, 1 exponent button, negative button, and 5 basically will get you there. If you're going non-display, you would start with the number, which would mean 1 exponent button, negative button, and 5. Then you would hit the log button, and then you would hit the negative button to make it positive, basically. So those are the two ways that you typically would punch it in. All right, so we have 5 on there. So should we record it as 5, 5.0, 5.00, 5.0000? Lots of zeros. I feel like that's too many zeros. So I can limit it down. Which way is the proper way to report this answer? It is 5.00 in this case. And again, it is because when we look at the concentration, it has 2 significant figures. So 2 significant figures means not 2 significant figures in our answer, but 2 decimal places in this case. So again, we're going from significant figures to decimal places. And again, backwards would be the same thing, as I mentioned earlier, decimal places to significant figures. Any questions on that there? And by the way, the name here, pH, does tell you what you need. You do need the H plus concentration basically to calculate that. So that tells you what it is. By the way, this would be acidic, basic, or neutral. This one would be. This would be acidic as it is less than 5. You should always look at the pH value when you're doing that because that's usually what the scale everybody has in their head. And by the way, when you are asked that question, is it acidic, basic, or neutral? There is only one answer. Cannot be acidic and basic at the same time. Although I've seen that on many exams, things being acidic and basic. I haven't really seen anybody do all 3, acidic, basic, and neutral. So I guess that's good, but it can only be one of those things. So why don't we do that here? Let's try it out. What's the pH here for each of these solutions separately? So these are 2 different problems. And are these guys acidic, basic, or neutral, these guys? So 2 different problems, looking for the pH in each. And again, are they acidic, basic, or neutral here? Okay, so let's take a look. We'll start the first one here. We have the H plus concentration given to us, so we can go right into our pH equation, negative log of the H plus. That's going to give us negative log of, in this case, 2.1 times 10 to the minus 5. Again, punching that into your calculator correctly, hopefully negative log 2.1 negative 5. Going to give us here a 4.68 pH. Once again, 2 significant figures, 2 decimal places coming out here. That's going to be acidic, basic, or neutral. This one's going to be. It is going to be acidic as it is less than 7. Any questions on that one there? Looking at the second one, we are calculating the pH, which is minus the log of the H plus concentration. As I mentioned before, it tells you what you need, but in this case, we do not have the H plus concentration. We do have the OH minus concentration. So perhaps one approach here would be to use KW like we did previously to actually get the H plus concentration. And if you do that, 1 to the minus 14 divided by 5.9 to the minus 8, gonna give you here a 1.7 times 10 to the minus 7 molar. Now that we do have the H plus concentration, we can calculate the pH. 1.7 times 10 to the minus 7. And that's going to give us here 6.77 as our pH. That means that this one's going to be slightly acidic. Yeah, as it's less than 7. By the way, if you ended up with this answer by just popping in there the number that was given to you, and you ended up with this number of like 7.23, that is obviously not the pH in this case, but it is something. So you're only a couple of slides early. That is the OH minus, so this is what is known as the POH in this case, which is not necessarily a bad thing to calculate because, as we will talk about, as we will see, and we'll just jump a slide or two here, if you take the pH plus the POH, it equals 14, which means that if you wanted the pH at this point, you could take 14 minus your 7.23, and you will get to your pH. So not necessarily a bad thing, but remember that it is not the pH that you would have calculated. And once again, it tells you what you need. POH, you need the OH minus concentration. Any questions on that there? So as we see there, the pH scale is based on the log of 10. And what we see in terms of the pH is for every 1 pH that changes, the power of 10 of the H plus concentration changes by 1. By the way, if you have the pH of 1 times 10 to the whatever, it's always whatever the exponent is will be the pH if it's 1. So if you have pH of 3, you have an H plus concentration 1 times 10 to the minus 3. If you have a pH of 4, 1 times 10 to the minus 4. As the H plus concentration goes up, by the way, as we talked about, the OH minus concentration goes down, and we do see the pH go down, and vice versa. As the H plus concentration goes down, we see an increase in the pH, or the OH minus concentration, and the pH will also increase in that particular case. Remember, again, the H plus OH minus run opposite of each other. As one goes up, the other goes down. And again, it's that different concentrations of those guys in the solution that determines whether or not it is acidic, basic, or neutral. And by the way, technically a pH of 7 is neutral because that is when those concentrations are equal to each other, and they both will have a concentration of 1 times 10 to the minus 7, which if you then calculate the pH, it is a pH of 7 at that point. So for us in here, just to keep it straightforward, we're going to go with 7 on the nose. It's got to be neutral or very, very close, like, 6.999 or something like that. It's got to be really, really close to 7 to be neutral. Otherwise, if it's slightly above 7, it's going to be slightly basic. Slightly below 7 will be slightly acidic. Any questions on that there? Now, there are different ways to measure pH. One very common way is a pH meter. pH meter gives you the actual pH of the solution by taking the electrode here. The electrode measures the H plus concentration in the solution, and it will give you a pH range. The way it really works is you give it a solution that's like a pH of typically 4, 7, and 10. And you calibrate the pH meter, and it goes, okay, the voltage for like a pH 4 solution is this, the voltage for a pH 7 is this, and the voltage for a pH of 10 is this, and it makes like a calibration curve. So then when you put your solution in, it goes, okay, it's got like this voltage, that's like a pH of 6 point something, and it does like a little calculation. Could also use pH paper like we might do today. It's kind of like if you ever done like a pool test strip type of thing, and it's got all the little boxes and it changes colors. You try to match it up with the scale there to find the best color. It's not really the greatest thing. Obviously, it will kind of an estimate by matching up the colors. We also sometimes will use litmus paper, and it will not really tell us the pH or anything like that, but we use litmus paper more to figure out if something's acidic or basic. And again, it doesn't really give you a pH value or anything like that. But if litmus paper typically turns red, it means it's acidic. And if litmus paper turns blue, it usually means it is basic. So once again, it doesn't really give you the pH, but it does tell you if the solution is acidic or basic. Here's our pH scale, and as we talked about there, we see some strong bases up there, about 14, strong acid around 0. We have pure water around 7. By the way, the pH of water that's not pure water, maybe water's been sitting out a while, is it 7? Actually will not be 7 because it'll pick up some carbon dioxide in the air, and that will increase the H plus concentration. So, you'll find water right around there sometimes, and people are surprised that it's kind of like more acidic in that, especially if it's been out a while. Again, it creates like a carbonic acid that increases the H plus concentration and actually lowers the pH more than it would in a pure water situation. Now, as we just talked about a second ago, there are similar scales to pH. and the popular one there is the POH. And again, you do need the OH minus concentration. The good news is it's pretty much the same calculation. So we have our POH calculation. We obviously have our pH calculation. And we have our relationship that we talked about there, which is the pH plus the POH equals 14. So it does give you a little bit of variety in terms of how you could solve these problems. By the way, we also have still our KW that if you wanted to use like we did in that problem as well, you could go the KW route. So like I said, there can be, a few different ways to solve the same problem. They all should really give you the same answer regardless of which way you choose. And let's add a couple more to this because why not? So if you do have the pH, from the pH, you could get directly from that number the H plus concentration. And you can calculate the H plus concentration by taking the inverse log of the negative pH. Now, I will say on most people's calculators, when you hit inverse log, your calculator will oftentimes put a 10 and a caret up, and you want to make sure it's negative pH. That's how some people do scientific notation incorrectly, which is why you'll be in real trouble here if you do it still that way. You could also do the same calculation for POH. From the POH, you could get directly the OH minus concentration, and that is the same thing. That's the inverse log of the negative POH. And once again, on most people's calculator, that's going to pop up something like a 10 and a caret, negative POH. How do you get to the inverse log? I would say on most people's calculators, upper left corner, there's a second button or a shift button, one of those in the upper left corner. And then usually right above your log button, you'll see like a 10 to the caret or like a 10 to the X sort of above it. And that is your inverse log. So once again, just like the other formula, you will, depending on your calculator, as how you would put it in. If you have a display calculator, you would do the second or shift button, probably the log button. You would then hit your negative button and then pop in like your pH or your POH, whichever one you're doing. If you have a non-display calculator, you would run backwards like all the other ones that we've been talking about. So you would do actually your pH or your POH, then you would make it negative. Then you would hit your second button, and then you would hit your log button. So again, depending on which way your calculator is running, that is how you would put in the top part. So people always get confused about what equation to use where. So if you have the concentration and you want the pH or POH, it is these equations pretty much. If you already have the pH or POH and want the concentrations, it's the top equations here. So again, that is typically what we use for these things. Any questions on that there? This is also where people will give the bad answer of this solution is acidic basic at the same time. And it's because people will calculate the pH and go, cool, it's above 7, so it's basic. Then they'll calculate the POH and go, cool, it's below 7, it's acidic. And before you know it, the thing is both. And it's not, shouldn't be both. I would highly recommend you should always look at the pH scale because frankly, that is the one that most people have in their head. And once again, the pH scale runs from 0 to 7 to 14, where this is basic, this is acidic, and this is neutral. And the reason why you shouldn't use the POH scale is because it is actually opposite. Below 7 on the POH scale is actually basic. Above 7 is acidic. So like I said, most people have this in their head, which is why you should probably go with that scale, as the POH scale is opposite. So if you have a large pH or a high pH, you will have a low POH and vice versa. So they do run opposite of each other. Pretty much everything on this page you do. So let's practice some of this, make sure we can punch things in our calculators. All right, we got 2 solutions here. For each of them, let's just do it all. Yeah. So what is the pH? POH. So we'll do pH for this guy, POH. Let's do the OH minus concentration. And is it acidic, basic, or neutral? For the second one, what is the pH, the POH, and what is the H plus concentration? And is it acidic, basic, or neutral? So calculate everything. Okay, so let's take a look and see here. So start with this one here. So we're basically looking for everything. So because I have the H plus concentration, I really do have a couple of options or routes to go with. I can directly from that get the pH. I could also use KW and get the OH minus concentration. So it really is your choice, whichever way you want to go. I'm going to go with pH first. So I'm just going to go right into the pH here, minus the log of 3.6 times 10 to the minus 9. And that's going to get me here minus the log, there we go. 3.6 to the minus 9. That's going to give me a pH of 8.44. Now that I have the pH, I could very easily get the POH by using the relationship we talked about, that basically when you add them together, they equal 14. So that means that the POH in this case would be 14 minus the pH of 8.44. That is going to get me a 556, looks like. So that is halfway done. At this point, I now have two options to get the OH minus. I could still use KW, but now I could also, because I have the POH, use that new formula that we just saw. So that's the one I'm going to use. I could take the OH minus concentration, and that equals the inverse log of the negative POH. So once again, on your calculator, when you punch that in, it probably will look something like this. And again, if you do that correctly here, you will end up with, we'll call it 2.8 times 10 to the minus 6. Does need molarity as it is a concentration. It also has 2 decimal places, which means we should end up with 2 significant figures when we do that. By the way, if you wanted to use KW, you could still use KW, which would mean OH minus is equal to 1 times 10 to the minus 14 divided by 3.6 times 10 to the minus 9, and that will get you there as well. Any questions on any of those calculations there? By the way, this is acidic, basic, neutral. This is going to be basic, always looking at the pH, so this definitely will be basic because of that. Any questions on that one there? All right, looking at the next one that was there, we have, in this case, the OH minus concentration. So again, you have two options like the other one. You could go directly and get the POH. You could also go directly and use KW to get the H plus concentration. So in this case, I'm going to go POH first, kind of like what I did previously. So the POH here is minus the log of the OH minus concentration, and that's going to give me minus the log of 9.2 times 10 to the minus 2. And that will give me a POH in this case of 1.04, I think. I am again going to use that relationship that the pH then would equal 14 minus the POH. So that's going to be 14.4, and that is going to get me there a 1296 in terms of my pH. And at this point, that then opens up two options to get to the H plus. And once again, you can take that the H plus is equal to the inverse log of the negative pH, which again would look something like this on your calculator. Going to give us a, we'll call it 1.1 times 10 to the minus 13 molar here. And once again, if you chose to, you could have used your KW as well, which would have been this calculation. Obviously, you don't need to do both, but you could have done either option in that case. Any questions on that? Just like at that point, if you got the H plus first, you then could have used that with the pH equation and got the pH that way instead of subtracting from 14. So again, there's a number of options. In this case, this one is going to also be basic because the pH here is above 7. Any questions on any of those calculations there? All right. Let's do a few more here, just to make sure. All right, the pH of a solution is 5.67. Let's just do all this here. Also do the H plus, the OH minus, and is it acidic, basic, or neutral? All right, so let's take a look. We got pH, so I'm going to go POH first here, which was the original question. So minus the log, not really. We'll do our POH is equal to 14 in this case, minus our POH, our pH. And that's going to get us 14 minus 5.67. And that will say 8.33 as our POH. In this case here, I could get my H plus concentration by taking the inverse log of the negative pH. So that's going to be, in this case, a 10 carat negative 5.67. And that will get me a 2.1 times 10 to the minus 6 molar. Now that I have the H plus concentration, I could actually use KW if you wanted to, or you could do the same calculation using your POH that you also have at this point. So that's going to be the inverse log of the negative POH, 10 carat negative. I feel like I hit the wrong number in there. Did I? 14 minus 5.67. I did. That stuck up. 8.33 would be better on that one. There you go. If it can't both be the same number. All right. So negative 8.33 on that one. That's going to give us a 4.7 times 10 to the minus 9 molar. Once again, here, 2 decimal places, 2 significant figures going the other way. This would be acidic, right? As our pH here is less than 7. Question on any of those calculations there? All right, so why don't we just do, let's just do what it asks in this one. What is the H plus concentration of this one? All right, so on this one, once again, the pH does tell you what you could get from it, which is the H plus concentration. And again, that's going to be like we've been doing, our inverse log of the negative pH. Going to look something like that, probably on your calculator. And that will get us a 7.2 times 10 to the minus 4 molar in this case. Yeah. A question on that one there. All right. Then let us talk about, we kind of did that example actually. Let's talk about the pH of a strong acid and even a strong base. Now, in a lot of these examples, obviously, we've been given more like a generic, like H plus or OH minus concentration, but you could be given and being asked what is the pH of a strong acid or even a strong base. And remember that our strong acids, there's kind of that list that you should know, which is again hydrochloric acid, nitric acid, sulfuric acid, perchloric acid, hydrobromic acid, hydriodic acid. Remember that a lot of our strong bases are things like sodium hydroxide, potassium hydroxide, hang right there at potassium, a little calcium hydroxide, and go downward, strontium hydroxide, all those kind of guys are sort of, along with lithium hydroxide as well, are strong bases. So what we would want to know is because they are a strong acid or even a strong base, that means that they're going to 100% break apart into their ions, which means essentially in terms of pH, the important thing would be the H plus concentration. If we had something like a strong base, it would completely break apart into a sodium ion and a hydroxide ion. Now, in terms of pH, it would actually be the hydroxide that would be important because that would allow you to get to the pOH and then into the pH equation or formula. So if we had something like 0.1 molar hydrochloric acid, we know, as we see up here, that that's going to completely break apart into H plus and Cl minus. It is a 1-to-1 relationship between the whole thing and the H plus, which, as we talked about with concentration, means that essentially our H plus concentration is going to be 0.1 molar. That means our pH in this case would be minus the log of 0.1 molar. And that's going to give us our pH there of 1 in this case, which is acidic. So if you do have a strong acid, you need to figure out what the H plus concentration is, and then you could go into the pH. Good news is most cases it's going to be probably the same number. If you have a base, you need to figure out what the concentration of the OH minus is, so you could go into the pOH and then subtract 14 and get to the pH. If it is a weak acid or weak base, what you should do is wait until you get to Chem 1B, and then you'll know how to do it at that point, because we definitely don't do that in here. All right, so for each of these, what should be the pH of these solutions? Take a moment there. They're both is going to be a strong acid, as it's one of our on our list there. We'll break apart into H plus and perchlorate here. And the whole thing here is 0.025 molar. It is a 1-to-1 relationship between that and the hydrogen, which is what we really need to get to our pH. And so that means it's going to be the same in this case. And that means that our pH will be a negative log of 0.025. And in this case here, going to give us a pH of 1.60. Which is negative there, and not negative, which is a acidic, is what I'm trying to say. And that does make sense. When we look at a strong base here, it will also break apart. But when it breaks apart, we will get a calcium ion and we will get 2 hydroxide ions. So that means when we look at the concentration of the whole thing, it is the hydroxide that we're interested in, and it's actually 1-to-2 relationship, which means, as we talked about with concentration, we do have to actually multiply the concentration by 2 here to get the proper hydroxide concentration, which would be 5 times 10 to the minus 2 molar. Now that we have that, once again, that is still the hydroxide concentration, which means you actually have to calculate the pOH first. And if you do that, you got a pOH of 1.30. The pH can then be found by subtracting 14 from that number, or that number from 14. And that will then get us a pH of 12.70, which does make sense. And that is basic in this case. So I would say probably more so the strong bases, you might have to adjust the concentration of the hydroxide more than the strong acids, since sulfuric acid is the only sort of diprotic acid. All of the rest of them are monoprotic, which means they're pretty much going to be the same concentration for the strong acids. Any questions on what to do with a strong acid or strong base? I would say, again, in this class, if you see an actual formula for an acid or base, you could probably assume it's going to be strong, since we do not do the weak acid or weak base calculation, which is a fairly good long calculation. Any questions on that there? Next thing we're going to talk about are buffer solutions and what a buffer is and how a buffer works. So first off, a buffer is a solution that actually will resist changes in the pH, even if you add more acid or base to it. So a very big misconception that people have about a buffer solution is it is a neutral solution. And a buffer solution can be neutral, but it could also be acidic or basic. You could actually make a buffer at any pH you want. So any pH you want, you can make a buffer solution. So what that means is if you made a buffer solution at a pH of 5, for example, that means that when you add acid to that buffer, the pH should stay roughly around 5. It will go down a little bit, but it will not jump pH a lot. So it won't go from like 5 to a pH of 1. So it won't have a big jump in pH. It basically will hang around 5. It'll come down a little bit, but not a lot. And if you have that buffer and you added base to it, the pH will basically still stay around 5 and may go up a little bit, but it will not jump from like a pH of 5 to like a pH of 12 or something like that, where a really big jump in pH. And the way a buffer is able to do that is basically what it is made out of. A buffer has to be made out of a weak acid and is sometimes referred to as the salt of its conjugate base, or you can make a buffer out of a weak base and the salt of its conjugate acid. Those guys are related to each other through the Bronsted-Lowry definition of 1H plus difference. And really the reason that is because a weak acid or a weak base is a weak electrolyte, which means when you take something, for example, let's say you wanted to make a buffer out of HF and NaF. That is a weak acid, and it is the salt of this conjugate base. The salt just means that there's a sodium there. The sodium is really not important. It is actually the F minus part that is the buffer part of it. So if you take a look at the difference between HF and F minus, the differences are 1H plus, like we talked about with Bronsted-Lowry. What that essentially means is when you make a buffer out of that, you will have the HF with the arrows in the solution, not really, but we'll kind of do this. And what you will have in that solution, if this is your buffer, basically, is you will have a base part to your buffer and a acid part to your buffer. And that's really important for how a buffer works is they both are actually in the solution to begin with. The reason you cannot have a buffer that's made up of a strong acid or strong base, if you wanted to do the same thing with like your hydrochloric acid, which, you know, has H plus and Cl minus, right? When you put that into your solution, you pretty much will only have H plus and Cl minus. So you'll have like the base part, but you are missing the acid part of the buffer that makes it functioning. So anything that is a strong acid or strong base cannot be a buffer. So if you see anything that's on that list of strong acids or strong bases that we talked about, and they're like, can this be a buffer? The answer should be no. And if it's not on those lists of strong acid or strong base, and it's like an acid and base, it can be a buffer as long as they're related to each other by 1H plus. There will be some extra things like a sodium sometimes, a potassium, but it's not really doing much here. So that's really important for how a buffer works, is to have both of those things in there. So let's talk about really how a buffer works. Let's start with how a buffer works when it's not a buffer. So if we take water, which is not a buffer, and we take some water here, which is not a buffer, and we decide we want to add hydrochloric acid to it. When I add hydrochloric acid to water, it is going to completely, as we talked about, break apart into H plus and Cl minus, which means when you add that HCl to this water, you're going to generate a lot of H plus and some Cl minuses. Remember, none of the HCl units will stay together. That just made a lot of free H plus, right? And that's really important because the pH is equal to negative log of the H plus concentration. That means that our concentration of H plus in that water just went up by a lot. And if my concentration of H plus goes up a lot, the pH should then go down by a lot. So in this case, you'll have like your water at 7, for example. You got nice pure water. You add some HCl, it'll go from like a 7 to like maybe a pH of 2 or 1. A really big jump in pH because you added a lot of H plus very quickly. Now, if we take our same water here and we add a strong base to it, like sodium hydroxide, it will also 100% break apart into sodium ions and hydroxide ions, which means in solution, you'll have a bunch of sodium ions, which is not going to do much to the pH. But what's really going to sort of affect it is you now made a bunch of hydroxide ions really quickly. What we know about the hydroxide ion is as its concentration goes up, the H plus concentration goes down. The result of this is our pH should go way up because we made a lot of free OH minus in the solution. So in the case of water, if you started like a pH 7, add some strong base to it, it'll jump from 7 to like maybe 10, 11, 12, a really big jump in the pH. So this is what happens when you add a strong acid or strong base to something that is not a buffer like water. Any questions on that? So let's see what happens if we take the exact same things and actually add it to a buffer. And we'll use this guy as our buffer example. So remember that when we have this buffer to start with, we have really our equilibrium here set up. And again, we have our base part of our buffer and our acid part of our buffer. So now if we take that same HCl and add it here, and HCl is obviously a source of H plus and Cl minus, right? When I add HCl to this buffer, it is going to react with the acid part or the base part of the buffer. Which one do you think? They're called acid, what type of reaction? Acid base reactions, right? Which means when you add this HCl to this buffer, it's actually going to react with the base part of the buffer, which is the sodium fluoride. And again, that is the base part of our buffer. That's our acid part. And we're going to get a double displacement reaction that's going to happen here. We will get HF and we will get a little sodium chloride made. So what happens in this case is a couple things that's interesting. As you might see, we actually created more of the buffer that we started with, which always happens. So when you add something like an acid to a buffer, you actually will use up part of the buffer, but make the other part of the buffer in return. We also made sodium chloride, which is a neutral salt. So that is a neutral salt. But it is actually what we don't see here that we did see when we added it to water. What did we see when we added HCl to water that was on the product side? We saw a lot of H plus being formed. And in this case, we have no free H plus being formed. And that is because when you throw this in, this H plus goes and finds the base part, and it actually will make some of the acid part of the buffer in this case. And because there is no more free H plus, the amount of H plus that was there to start with, concentration of H plus stays relatively constant. And because the amount of H plus that was there to begin with stays relatively constant, that will keep my pH relatively constant as well. Question on that. So what happens here if we add our to our buffer our strong base? So if we take our sodium hydroxide and we add it here, which is a source of sodium and hydroxide ions, if I take my sodium hydroxide, it will react with the acid part of my buffer, which is the HF. And that means that I will make some sodium fluoride in a double displacement reaction, partner switching, and we will make water in this case. Once again, what we see is we made part of the buffer that we started with. We also made water, which is not going to screw up the pH. What is really important here is what we do not see. What we saw when we added it to water was a bunch of OH minus. In this particular case, we have no free OH minus being formed. And that is because when we add this, the OH minus will actually, again, react with the HF and produce, in this case, water. And that means no free OH minus. So the concentration of OH minus stays relatively constant. And because H plus is tied to that, the H plus concentration will stay relatively constant. And thus our pH will also stay relatively constant. I say relatively constant because if you're really following it, your pH, for example, will go up a little bit, but it will not have a really big jump in pH, or your pH will go down a little bit, but not have a really big jump in it. So ultimately, how a buffer works is because it has an acid part and a base part, when you add additional acid or base to your buffer, it prevents the formation of free H plus, it prevents the formation of free OH minus, and both of those things is basically what will keep the pH relatively constant. We won't see really big jumps in pH. Again, you'll see very small movements if your buffer is good, but you will not see these really big jumps. Question on buffer there. Just to finish out real quick on this, if you have a buffer, a lot of times you want to kind of make your acid part and your base part of your buffer relatively equal to each other. And that's because when we add acid, it will use up some of your base part, but it will make some of your acid part. So acid part, dramatic drawing, a base part of our buffer will happen. And if you add base to your buffer, it will use up some of the acid part, but make more of the base part here. And there is a limit to buffer, sometimes referred to as buffer capacity. What happens if I just kept adding acid to my buffer? Every time I add acid, I'm going to use up some of my base part, right? So if I just keep adding, eventually I have no more buffer ability, right? Because all the base part of the buffer is gone. And that means if you continue to add acid, you're now going to add a lot more H plus, and you're going to see a really big jump in pH at that point because you blew through your buffer. It's also really important when you make a buffer that it's the correct molarity, because if you grab off the shelf, for example, 18 molar hydrochloric acid, thinking you're adding 0.1 molar, hopefully that doesn't happen today, you will blow right through it because your buffer is not set up, for example, to handle that unless you did make it set up to handle that. So concentration of buffer is really important, the concentration of the acid and bases that you're adding, and there is a limit to how effective a buffer could work. But it does work really effectively if you do it right, because you're sort of regenerating part of the buffer as you use part of it every time you kind of do it. And you can kind of go back and forth and sort of regenerate parts that you need. And it can resist changes pretty well as well. Any questions on buffers there? All right, we will wrap it up there. Examine